in chapter 20, can you guys tell me some of the things that we kind of talked about and learned about charges and how they interact with each other? Yep, opposites attract. Negative wants to go to positive. What about like charges? They repel each other. Good. Um, how does the electric field um, kind of work as I get closer to a charge? It increases in intensity, yeah, and so the forces due to the electric field increase as I get closer to a charge, and then those forces are not so strong when I get far away from a charge. And so we're going to kind of start out with what we did the other day, where I give each one of you questions. And so I'll let you read through, and you can either call dibs on these first two, the second one, or the third one, so take a look at them. And this is a review from first semester. And we'll call it 1, 2, and 3, and call your dibs. Ned has 2. You're able to use your book here. Okay, Lisa has 3, Gabe. 1 it is. Yeah, energy is like a fuel of some sort. And it's what allows us to do work. Which is moving things around. Right? Anything. What types of energy have we talked about already? Ooh, kinetic. Gravitational. What else? Static. Yeah. I'll give you static. Lisa, Ned, can y'all add to that list? Other types of energy we've talked about? Uh-huh. Like gravitational potential. What other kind of potential have we learned about? Gravitational potential. What type of potential energy is in food? Chemical, yeah. And then what kind of energy does your body make with that food? Ooh, kinetic, and after you do a little bit of kinetic, you make a lot of thermal. Yep. Good. Okay. That's a pretty comprehensive list. What law do we already know about energy? Conservation. Yeah, good. Uh, that's okay. It's okay. I'll give you both credit for it. So the conservation of energy, which is that all of the initial energy is equal to the final energy. And remember how much fun we had with the gravitational plus the kinetic energy initial is equal to the gravitational plus the kinetic energy final? Bringing it back. And then what is work in relation to energy? So, okay, I'll give it to you. Sum of work done by each force. Um, that works. And so I'm going to phrase it a little bit differently. It's the total change in energy. Or you could say that it is force times distance. What is energy measured in? Do you guys remember the unit? What was it? Joules. Do you remember what watts was measured in? Oh, I'm sorry, work. Watts. Right. Gave it away. And so today we're going to kind of build on these ideas. This is all the refresher that you really need to know. We'll go into a little bit more detail about kinetic energy. But energy is the ability to do work and move stuff around. There's a lot of different kinds of energy, but no matter what kind of energy we're dealing with, it's always conserved. It's never created or destroyed. It just changes forms. And then energy has the ability to do work, which is move stuff around. And so we're adding a new kind of energy to this, which is the electric potential energy. And so this is a form of potential energy, right? We dealt with gravitational potential energy, but now we're moving on to electric potential energy, and we write this as U elec, E-L-E-C. If you have some other symbol that you want to use for it, that's okay, right? Electric energy is potential energy because we can store a buildup of charges. What have we already learned about that can store a buildup of charges? Everything. Everything can, right? From the balloon that you charge on your hair to water, parallel plate capacitors, cells store a buildup of charges. And so this happens everywhere in nature. We've got cells, a battery is stored electric potential energy. The positive end of a battery literally has lots of positive charges, and the negative end literally has lots of negative charges. And it's that difference that creates the potential. Clouds in the earth, we know that when those clouds rumble around and there's friction up there happening, there's an exchange of charges and in the atmosphere, and that creates an overall positive and negative kind of balance and interaction. And then parallel plate capacitors. Can you guys summarize for me what a parallel plate capacitor is? We talked about it. Good, yeah. It's like a line of positives and a line of negatives. And so it's literally just two metal plates. Typically we hook them up to a battery, right? And that induces a charge on both of those plates. One positive, one negative, equal and opposite. Electricity does have the ability to move objects. Specifically, what does electricity move? Electrons. Good. Mostly electrons. Can it move other objects? Yeah. What did we see it move when we were playing the other day? Yeah. Hair. What else? Water. What else? Paper. Right. Basically anything, right, that has a charge, it can move. And so today we're going to kind of talk about the possibility of electricity moving things and how that works in terms of energy. When I've got a collection of charges, and we'll call this a source charge, it has a lot of positives, right? Firstly, what do we know about positive and positive charges? They don't like each other, right? They repel. What do we know about the electric field and positive charges? It goes outwards from positive charges. And so the electric field pushes out from our source. You can think of it as a push because it's a force. How strong is the electric field if I've got an object that's far away? Not very, right? And so the greater the distance they are apart, the electric field is weak. What would happen if I moved this closer? If I took this little point charge and moved it in? Yeah, the electric field would be stronger, right? And so when I move it closer, these short distances give me an electric field that is strong, right? And so if we think about that in terms of a push, right? Where am I going to have to push this little proton with the most force? When it's close to or far away? Yeah, when it's close to it, right? Because this is starting to push back. And I'm going to have to apply a little bit more force to get it closer. Does that kind of make sense? Okay. Let's say I have these 2 point charges, right? One's only got a 1 positive and one's got a 3 positive. Which one am I going to have to apply the most force to make it stay there? The 3 positive. Why? Yeah, because it's got a bigger charge. So it is going to push back, right? with a greater force than just this little puny 1 charge. Right? And so the magnitude of the charge does make a difference, as well as the distance from the source. Right? And so, of course, we've got a formula to describe this. We say the electric potential energy is equal to the charge of the particle Can charges be negative? Yes, like what? Electrons. Yeah, those have a negative charge. And then we're bringing in this new and very confusing variable called the electric potential. Okay. This is confusing for 2 reasons. One is the electric potential is not the same as the electric potential energy. It has to do with it, but it's not the same. The other kind of confusing thing about this variable is we've used V for volume. We also use V for volts, which is what electric potential energy is measured in. Okay. The electric potential, though, is just kind of a constant for an electric field and where you stand in that field. Right. And so electric potential energy, this is measured in joules, just like any other energy. Charge in coulombs we've dealt with. And then this electric potential is in volts. It's actually in joules per coulomb. This is a compound unit, joules per coulomb. But we don't say joules per coulomb, just like we don't say Newton meters. Instead of joules per coulomb, we call it volts. And so this constant, the electric potential, is like the potential to have potential energy. I know. And then so I've got this source, right, where the electric field is very strong, close to it, and it's a little bit weaker far away from it. And so what we say is that the electric potential right here, that V constant, is going to be greater than out here, right? The potential to have potential energy. Now the actual potential energy is determined by what kind of charge I put here. If I put a 3+, I'm going to have a lot more potential energy than if I just put a 1+. Does that kind of make sense now? And so the electric potential is just about position to the source, right? It's greater when you're closer, it's less when you're farther away. So these potential differences can actually create movement and energy. Usually a delta V, an electric potential, is created by a separation of charges. And so this looks a lot like a parallel plate capacitor. I've got all the positives on one side, all the negatives on the other. What do we know about parallel plate capacitors and the type of electric field they make? They make a uniform field, and does the field go from positive to negative or negative to positive? I couldn't hear you. What is it? Other way around, positive to negative. So electric fields always move from positive to negative, right? And so we say the potential difference, or the electric potential difference, is the difference in potential at these 2 points due to the electric field, right? If I place a positive charge at one of these points, it's going to experience a much greater push here than it is here. If I put a negative, it's going to experience much greater pull here than it is here. So what would happen to a positive charge if I put it at point A? Which way is it going to move? To the right? Positive and positive like each other? To the left. Yeah. Right? And so that positive is going to go where it's attracted to. What direction would I have to push if I wanted to move the charge to the right? So let's say I want to take this positive and I want to move it to the right. Do I have to push to the right or push to the left? Yeah, I have to push to the right because it's wanting to go to the left. And so I'm going to have to apply an opposite force to get it over to the right-hand side. Right? What would happen if I put a negative at point A? Yeah, it would go towards those positive charges because negatives like positives, right? If I wanted it to not just zoom at any old rate over to the positive plate, what would I have to do? Yeah, I would have to kind of like put my hand here, right, and block it and then guide it along at whatever pace I wanted. And so I'd have to push in the opposite direction because naturally it wants to go that way. Likewise, if I wanted to move this negative charge over to the negative plate, what way would I have to push? Say it with confidence. Yeah, to the left, right? Because these two are going to oppose each other, and so I'm going to have to apply a force to get it over to the left. And so kind of knowing those interactions, we're going to talk about the conservation of energy. The initial kinetic and electric energy is always going to be equal to the final kinetic and the final electric potential energy. This is nothing new. If I want to talk about the change in kinetic energy or the change in electric potential, right? This delta V is not potential energy, but just electric potential. And then I've got this formula that I can use. And so if I say, you know, an electron is traveling at 500,000 meters per second squared, what is the change in electric potential? You would be able to do that because you know the mass of an electron, you know the velocity at which it's traveling, right? That is equal to its kinetic energy, which would come up here. You know the charge of an electron, and so you would be able to tell me the change in electric potential. Does that kind of make sense? And so, velocity, yeah, that's a good question, is in meters per second. Mass is always in kilograms. And those are given to you in chapter 20 for protons and electrons. What unit do we measure energy in? Yeah, joules. And so we're gonna of course make it a little bit more complicated for you, but this K, the kinetic energy, is always going to be in joules. Kilogram. So 1/2 kilograms meters squared over seconds squared. Right, that's a compound unit. And joules is really good when we're talking about like people running or cars crashing or things falling, big objects. But joules is not totally appropriate for little tiny objects. And so we've got a new unit for you that you get to convert back to joules. So joules, again, is really good for those macroscopic things. It's not good for little tiny particles like electrons. And so what we're going to use is what we call the electron volt. Right. The electron volt is the amount of energy that it takes to move one electron across a voltage difference of 1 volt. And so if I've got, let's see, 2 plates, right? The delta V, the voltage difference, is 1 volt. It's the amount of energy it takes me to push this little electron from here to here. And so the electron volt is not a measure of voltage. It is a measure of energy. I know, I'm sorry. It's a measure of energy. So even though it has this word volt in it, which is about electric potential, this is a joule equivalent. And I promise we'll practice with these and get the language straight. But this is a conversion factor that I do expect you to not necessarily memorize, but at least have on your formula sheet. Alright, and so now knowing this, energy is measured in joules. It makes sense with the scale of things we're talking about to talk about electron volts. And so if I say, here for a problem like this, something starts with, or goes through a total energy change of 100,000 electron volts, right? In order to even begin to do these calculations, you've got to get that to joules, because that is what those require. Right? So just like whenever we are given centimeters, we always go to meters. You always turn electron volts into joules before you work with them. And then likewise for your answers will be in joules, but to make sense for what we're talking about, you need to go back to electron volts. Just like it doesn't make sense to talk about the size of a bacteria in meters, it doesn't make sense to talk about energy in joules for this kind of stuff. Okay, so let's take a break. Let's try number 1 on page 704, and number 5, 7, and 9 on page 706. Something like that, yeah. That'll be funny. He's coming in the middle of the video and we're in the middle of a sentence. So, so looking at this picture, right, on the left I've got an electric potential of 500 volts, and on the right I've got 400 volts, right? If I've got a positive charge moving from left to right, what's happening to the electric potential? Is it increasing or decreasing as I move from the left to the right? It is as simple as it seems. It's not a trick question. So going from 500 to 400, yeah, it's going to be easier, right? The electric potential is decreasing. When I have a positive charge in this space and it's moving from a high electric potential to a low electric potential, its kinetic energy increases. It speeds up. So what would happen if I placed a negative charge in here and moved it from left to right? Speed up? No? And if it's not going to speed up, what's it going to do? Slow down. That's okay. We're getting there. And so these are generalizations to make, right? So a positive charge moving towards a decreasing electric potential speeds up. A negative charge moving towards a decreasing electric potential slows down. Mm-hmm. And this is just frankly a matter of memorization. Alright, so if I take it and move it the other way, right? If I start on the right with this positive charge and I move towards the left, going up that electric potential, what's going to happen to the kinetic energy? Is it going to speed up or slow down? Yeah, it slows down, right? And so when it goes to increasing potential, a positive charge slows down. What about a negative charge? Speeds up. And so what we're doing is we're building a relationship between kinetic energy and electric potential energy. And so if I look at these, right, I know these generalizations that with an increasing electric potential, positive charge slows down, negative charge speeds up, decreasing potential, positive charge, speeds up, negative charge slows down. And then we also know these equations, right? That electric potential energy is equal to the charge times the voltage, that electric potential. And we know that energy is never, ever, ever created or destroyed. And so if I'm speeding up here, if my kinetic energy is increasing, what has to happen to the electric potential energy to make those equal? What is it? So if I have these two numbers increasing, can those ever equal these two numbers at base? Yeah, so it's got to decrease. They're inversely related. If kinetic energy is going up, electric potential energy is going down. Right? If kinetic energy is going down, potential energy is going up. Right. Right. No, yeah, you're thinking in the right direction. The other way you can think about it, right, was our roller coaster hill when we talked about potential energy. Where do I have the most potential energy on a roller coaster? At the tippy top, right? That's just a different kind of potential energy. And if I've got potential energy up here, is my person moving? No, right? But then what happens is they go down the hill. They lose the potential energy but gain the kinetic. It's a trade-off, right? And the same thing happens here with electric potential. If I've got a lot of potential energy, I don't have any kinetic. If I've got a lot of kinetic, I probably don't have a lot of potential. Same idea. This is just unfamiliar territory because we're not used to looking at electrons because we can't. Right. And so when we talk about the electric potential energy, right? Electric potential energy, as I get close to a positive charge, increases for another positive charge, right? And that makes sense because it's getting like more of that push from that positive charge, right? I'm having to resist with a lot of effort as opposed to if I'm far away. Conversely, if I've got a negative charge, I don't have to push so hard here, right? It's gonna move in that direction on its own. And so my potential energy is decreasing because its kinetic energy is increasing here. That kind of makes sense? So this one goes zoom, zoom, right? This one is pretty much trying to stay still. In fact, it's trying to go the opposite way. Very little kinetic energy, lots of potential electric, lots of kinetic energy, very little potential electric. Radius away from, right? And so as this electron gets closer, it's going to speed up. It's going to zoom, zoom, zoom. As opposed to when it's far away and it's only got that slight little attraction. And those are previous concepts. All right. We can talk about the electric potential energy and the electric potential of just point charges. And so if I've got a positive charge and a negative charge that are however far away, radius, I can find the electric potential energy and the electric potential. Right? Q is the source charge. Q prime is the other charge. And so the charge of the two of them, right, are K constant and the distance they are apart. This looks a lot like Coulomb's law. The only difference is we're not squaring the radius. Okay? And these are our two constants that we're working with, and that's just a reminder. I know, it looks a lot scarier than it is, but these are just plug and chug formulas. And so if I ask what is the electric potential energy of a proton and an electron that are 1 meter apart, okay, plug and chug those numbers. You can find it out. You'll get your answer in joules. You can change it to electron volts from there. Right? That's doable. Alright. We talk about the electric potential, which is V, right? The electric potential. In terms of how far you go away. And so the farther away that you go from a point, right, the lower the electric potential is going to be. And we express this in what we call equipotential lines. What does that prefix equi mean? E-Q-U-I. Or what's it sound like? Equal, or equivalent, yeah. And so these equipotential lines are where V is equivalent, right? We can say that at this line, very, very close to that point charge, I can say I have like a V of 10, right? 10. As I go out, my electric potential decreases all along the same radius. So we could say V equals 8, right? And then as I go even farther, all in that same radius away from the charge, my V is going to be even lower. We can express this a bunch of different ways. I don't like that way. We do talk about it in this way sometimes, but more frequently, you see it as the graph on the right, where your source is here, right? A very, very high electric potential. And then as you move away from it, that electric potential decreases. And we talk about those equipotential lines until it's almost zero at a very far away radius. Questions? I'm not going to ask you to look at a graph and tell me the electric potential or anything, just understanding how these work, right? When we look at a dipole, we've got a positive charge where we experience positive electric potentials, and negative charges where we experience negative electric potentials. As I increase my radius from the positive and from the negative, both of those approach zero. Why is this negative for a negative charge? Yeah, because it's going down. Because that charge is negative. And so when we talk about the electric potential in terms of a negative charge, we talk about it as a negative. V. Oop, V. The big thing I want you guys to know is equipotential lines, right? That all of this has the same electric potential. And that all of this has the same electric potential. Right? And so we can talk about electric potential energy and electric potential with point charges. We can also talk about them with capacitors. Yay! Right, and the capacitor is just that positive and negative. The voltage difference is the difference between 2 points. And we can ask those same questions, and so we can say, well, what is the electric potential at a given point? What is the electric potential energy or work done if I move from a point to a point? And then what is the strength of the electric field? Right, I can ask all those same questions that we've been asking about point charges with capacitors. The easy way to think about these problems is to set up a coordinate plane, and we do that based completely on assumptions, and so I'm going to tell you the assumptions that we make. These have an area of A, right, which is length times width. So L times W equals the area of the plates in A. Usually we're talking about square metal plates or round metal plates. And so if you're talking about circles, it's pi r squared. Right? The distance between these is distance d, usually a few millimeters, like 2 millimeters apart. any farther apart than that, and we don't get a whole lot of electric field going on because the distance increases, right? So we keep them close together. And then we call the negative plate 0. And so when we talk about the position on, I'll just draw an x-axis through here. On the x-axis, we call the negative plate 0. And so any distance out from that is a positive value and working its way towards the positive plate. And so I could describe a particle as being at like x equals 2 millimeters, in which case I know, okay, I'm talking about right here, right? And if I say I move from 2 millimeters to 4 millimeters, well, I'm moving that. Could we set the positive plate as 0? Yes, we could. It doesn't matter where you start your 0. This just makes a lot of sense. It's easy to draw. That's why we do it. There is no other rhyme or reason. Right, and so knowing these properties about capacitors and those assumptions that we make, more plug and chug, right? We've got the electric potential that we can calculate and the difference across the capacitors. We've got the electric potential energy, which is the same as the work done. And then we've got the strength of the electric field. What is the unit on the strength of the electric field? It's different than what we've been using. What's V measured in? Volts, yeah. What's D measured in? Meters. This is a voltmeter. We had been using newtons per coulomb, I believe. It's the same thing. This is what's standard in the industry, and so that's what we're using from here on out. So let's take a break. Let's try 15 and 19. And here's your homework for the chapter.